So let's talk about a really, really nice subject now as far as electromagnetic waves are concerned, namely guided waves or electromagnetic waves in waveguides. What's a waveguide? A waveguide is just a kind of hollow thing that can be of arbitrary shape, let's say a rectangular section waveguide, that extends in one direction to like quite big distances. Okay, so it's like it's a tube, it's a kind of rectangular section contraption whose walls are made of some material that has an electromagnetic response. Okay, so this is now inside like this, you see. We're going to take some very, very simple example case. So the walls are made of a perfect conductor. Now, because the walls of this are going to respond to the presence of electromagnetic waves by having some surface densities developing, the actual electromagnetic waves inside such a waveguide look quite different from the ones that you would get in vacuum. So how are we going to go about doing that? Well, the strategy is going to be quite simple. We're just going to solve Maxwell's equations inside the waveguide. Okay. So what we want to do, our quest, what we're after here, is really a solution of Maxwell inside the waveguide. Okay, and by now you know how this goes about. What we have to do is to find propagating wave solutions to Maxwell's equations with boundary conditions specified by the particular system we're considering. So in this case here, the boundary conditions are quite simple, because these things are made of perfect conductors. We know that the electric field parallel to all the surfaces has to vanish. And we also know that the perpendicular component of the magnetic field, so the component normal to the surfaces, this also has to vanish. Okay, this is the result essentially of rewriting our Maxwell equations in terms of boundary conditions like this. So so how are we going to go further? Well, we need a kind of solution form for our electromagnetic fields here. What we're going to do is focus on monochromatic waves for simplicity. So monochromatic waves for simplicity. Knowing that once we have the solution for a monochromatic wave, we can just do whatever spectral decomposition that we want by using the linearity of the equations to just combine the solutions together. Okay, so what we're going to do is take specified form for our fields. We're going to say that the electric field, which is going to be a function of the positions and of time, is going to have the form of a certain function of x and y with a waveform that has monochromatic time dependence like this. Okay, and now what do I mean? What do I mean by this? So in the axes here, I've taken, for example, that the propagation direction that we have here is going to be z, and then the other transverse directions are going to be like x, y, like this. Okay, so the propagation direction is going to be z in our system here, but the fields are going to depend on x and y. Okay. Because of this form, of course, we'll be looking for a similar solution for the magnetic field, RT. This is going to be some initial field, B0, which is also going to depend on x and y with e to the I kz minus omega t. Okay, and we'll specify these things later. Now, one of the things that's going to occur is that these waves inside here are not necessarily going to be without a longitudinal component. So we'll specify what this vector is here. So this is just something that depends exclusively on x and y. And in the z direction, you see the whole wave just has this very simple dependence here. So inside the wave, as I move along the wave vector direction here, I just get pure oscillations with wave vector k. But inside a slice at fixed z, the x and y dependence will be quite non-trivial. So how do we go about doing this? Okay, so let's just write our Maxwell equations inside the thing. So we, as usual, have Gauss's law. Now there are no charges in there, so this just vanishes. As always, the divergence of B, absence of magnetic monopoles, this is all zero. We have that the curl of E is once again dB dt, and the curl of B is equal to, we always write the mu 0 epsilon 0. Let's just write it straight in terms of the velocity of light, like in the book. So you recognize the equations: 1 over c squared dE dt. Okay, so so we want to find these E's and B's here. Here I should just put a little 0 to say that it's the function that I have here. We want to find E's and B's here, E0 and B0s, that solve the Maxwell equations. So what are we going to do? We're going to look for components of these things. So these vectors, E0 vector, we're going to write as 3 separate components: one in the x direction, one in the y direction, and one in the z direction. And similar for B0. Okay, these functions here are going to be functions of x and y. Yeah? So this is the component of the vector in the x direction, but this component is dependent on x and y. Okay, so I hope the notation is clear to you. Now let's just look at Maxwell's equations. So, for example, if we look at the condition of the curl of E, okay, you remember how to calculate that. I can just take the determinant of, so I would have x hat, y hat, z hat, dx, dy, dz, and then ex, ey, ez. So the determinant of that is really what I mean by the curl of E. So this should be equal to the time derivative of B that I have here. So immediately I can start writing a set of equations coming from this one. So I would have, if I do the z component, say I do the z hat component, I just need the these ones here coming through. So what that would give me is, for example, d ey dx minus dex dy. This should be equal to I omega bz, right? With minus sign here coming from minus I omega t. When I take the time derivative, I just get I omega. Okay, so similarly, I can do the other components. The other components look like this. So if I look at the x component, I would have dez dy, and then I would have dz of ey, but the z dependence is only in this exponential here. So that just gives me some ik, and then with the minus sign I get ik times ey. Okay, and this should be equal to I omega bx. The third component is going to be the one along y. Okay, so then I get the same equation here, but just with the minus sign and replacement of x for y. So I k e x minus d e z dx. This should be equal to I omega by. Okay, so so similarly, if I do the same with the curl of b, I get three more equations for the derivatives. Let's just write them down. So I get, once again, if I take the z component, it's like the same equations, but with e replaced by b, etc., and then a minus sign with 1 over c squared on this side here. So I get d by dx minus dbx dy is equal to minus I omega over c squared now, ez. And the other two components, the one along x here, so d bz dy. Once again, the z dependence of the by is just pulling out an ik. By is equal to minus I omega over c squared ex, and then ik bx minus dbz dx is equal to minus I omega over c squared ey. Okay, so maybe we just give little numbers, 1, 2, 3, 4, 5, 6, and we'll just discuss how to go further with this. Okay, so what do we want? We want to determine the electric field component-wise. So let's just start by computing, say, Ex. So where does Ex occur in our equations? Well, it occurs in this equation here, number 3, and also in equation number 5. So let's do a little manipulation. So the equation 3 tells us that Ex, I'm just isolating Ex in this equation here. So this Ex is equal to, let's see, I put this one on the other side, and then I divide by ik, so I multiply by minus I over k. So I have minus I over k times d ez dx. And then I had this term here, but I do minus I over k, so I get plus omega over k by. But actually, so if I look at equation 5 now, I can isolate by in this equation in order to replace it here. So from 5 I get that by. Again, I play the same tricks here. By, so I multiply by plus I over k, so I get omega over kc squared Ex. And then this goes on the other side. I do plus I, so I get a minus I over k dbz dy. Okay, so now I do, so let's say I call this equation, yeah, I can now substitute for this in here, right? So what I get is that Ex is equal to minus I over k dez dx plus omega over k times by, but by is this here. Okay, so what that gives me is plus omega squared over k squared c squared ex, and then minus I omega over k squared dbz dy. Okay, and now what I can do, you see, I can just isolate the ex, right? Because I would get 1 minus omega squared over k squared c squared ex is equal to this. So 1 minus omega squared over k squared c squared times ex is equal to just, I can factor out the minus I, say I do minus I over k squared factorization, and then what do I get? I get k times d ez dx plus omega dbz dy. So that tells me that ex is equal to, I can just take the minus sign into here, so I get omega squared, remultiplied by k squared everywhere, take the minus sign in, so I get I over omega squared over c squared minus k squared times k d ez dx plus omega dbz dy. Okay, so that's one handy equation for ex in terms of ez and bz. Now, so that's one of the sets. What we can do now is play the same game, but for ey. If I do the same game for ey, instead of using equations 3 and 5, I'm just going to use equations 2 and 6. Okay, and what I do when I do that is that I really just substitute x for y, and if you look at the signs, it's as if I was substituting omega for minus omega. So I can just like write that down straight. I would also have that ey is equal to I over omega squared over c squared minus k squared. And then I would have k dez dy minus omega dbz dx. Okay, so that's one set of equations. There are similar equations for bx and by, but let me just focus on E for now for simplicity. So now we have that the divergence of E must be equal to 0. And what that means is that if I look at the x derivative of Ex plus the y derivative of Ey, this must be equal to minus the z derivative of Ez. Okay, and now if I substitute these forms that I have here into this equation here, so Gauss's law, but in the absence of any free charges, because the inside of the waveguide is a vacuum. So what do I get? You see, if I take an x derivative of this, then I get second derivative with respect to x of E. So let's just do this. So I have I over omega squared over c squared minus k squared. And now what do I have? I have x derivative of this thing. So I get a k times the second derivative with respect to x of Ez plus the x derivative of Bz. But you see, when I add these two together, I get twice the dx dy, but actually added with a minus sign. So these terms will cancel. So the only thing that's left is the other y derivative of this, d2 dy squared of Ez, and the bz's have vanished. So that's the left-hand side. And if I look at the right-hand side, well, I just have that the z dependence is only in the exponential form of the free wave that we have here. So when I take a dz of the z component here, I just get this thing here, because these things do not depend on z by assumption. So I get an ik coming out. Okay, so I get that this whole thing should be equal to minus ik times the Ez. So if I simplify things a little bit, you see I can just get rid of the case here, because it's a common factor everywhere. The I can go, I can remultiply by this thing here and put everything on one side. So what I get is that the second derivative with respect to x plus the second derivative with respect to y, okay, and then just having remultiplied the factor, put this one there and then brought it back here, I get a plus omega squared over c squared minus k squared. All of this applied onto the z component of the field, okay, which is a function of x and y, must vanish. Okay, so this is the fundamental equation that we have here. Okay, and we get actually the same equation for bz of x and y. Okay. So this is the fundamental equation that we'll want to solve for our waveguides. Okay, there's some nomenclature associated to that. So if the z component just vanishes, you call that transverse electric waves. If the z component of the magnetic field vanishes, you call that transverse magnetic waves. And if both of them vanish, they're called TEM waves, transverse electric magnetic waves. Okay, but we'll see some example just in the next video, where we'll do a specific case in more detail.